Hello, everybody. My name is Sean Huddy. I work with CERIAS. Welcome to the fall 2024 session of the security seminars. I'm going to do a very brief introduction to CERIAS for those who may not be familiar with us. We're a standalone research and education center at Purdue University. We manage the cyber, physical, and cybersecurity ecosystem on the campus. We have faculty researchers that affiliate with us that do research in the areas of security, privacy, autonomy, resiliency, trustworthy and explainable AI, and trusted electronics. We also have a pseudo consortium of industry and government strategic partners that help us in ways of working with our researchers. They also work with our students for internships and job opportunities, as well as leading us in a strategic way. Then we also have students that affiliate, which what the slide on the screen is about. If you are interested in cybersecurity and want to learn more about CERIAS, we recommend that you take a picture of this QR code and register with CERIAS. It doesn't cost anything, and you will have access to scholarships, fellowships, internships, opportunities to meet with our strategic partners. Then we also have information on all of the student clubs around cybersecurity on the campus, cyber forensics, the Blue Team, CCDC, and ethical hackers. Then there's opportunities for those clubs if they go to competitions to potentially get travel grants through CERIAS. We have a 2-day annual symposium that will be April 1st and 2nd this year. Last year, we had 2 speakers from the White House. We had Heidi Shue and Daniel Ragsdale. We'll have workshops. And again, these speaking seminars, which you can also use to get continuing education credits. So if anybody is interested in CERIAS, please click on that QR code and join. It doesn't cost anything, and there are lots of opportunities. Thank you for your time. And now I'm going to hand it over to Dr. Karim. Thank you, guys.
Yeah, hi everyone. Welcome to the CERIAS Security Seminar. So my name is Imtiaz Karim. I am a postdoc in the Computer Science Department, and I will be the instructor on record for this course. If you have any questions or anything, you can definitely reach out to me. So we will start this seminar with a really interesting talk from Dr. Shagufta Behnaz, who is an assistant professor in the Department of Computer Science and Engineering from Pennsylvania State University. So the talk is about privacy and security in machine learning. So Dr. Mehnaz is an expert in this area. She has research focusing on the enhancing the security and privacy in machine learning techniques and model themselves. The most important or interesting thing is that she is a graduate of Purdue. She is our alumni. She graduated from Purdue University in 2020, and she was the recipient of a lot of awards. I don't want to go through all of them, but yeah, I will hand the floor to Dr. Mehnaz, and yeah, let's have a really good talk. And if you have any questions, feel free to ask after the talk.
Thank you so much, Imtiaz, for the kind introduction. So hi everyone, welcome to the talk. As Imtiaz mentioned, I am also a Purdue alumni, and I graduated from Purdue in 2020. And after that, I joined Dartmouth College briefly for a year or so, and then I moved to Pennsylvania State University, where I'm an assistant professor of computer science and engineering at our College of Engineering. Okay, so let's share the screen. Imtiaz, does it look good?
Yep, that looks good.
Looks good.
So today I'll be talking about privacy and security in machine learning, which is again my research area. And I will discuss that these have always been an afterthought and not a priority, because when we think about machine learning or artificial intelligence, we think about the functionality or utility of the models, and security, privacy come after that. So historically, it has taken only, the backseat rather than the front seat, but we will see the implications of privacy and security in ML or AI techniques today. And I know that this is the beginning of the semester, and many of you could be just joining Purdue University. So I will try to make a balance between the background of this security privacy issues in ML and also giving you some advanced information. But feel free to raise your hand or ask questions. I can take questions in the middle of the presentation or at the end, both are okay for me. All right, so let's start. I'll start by giving an overview of my research that is at the intersection of privacy, security, and machine learning. When I was a PhD student at Purdue, most of my work focused on how to improve security techniques using machine learning. So for example, how can we detect some anomalies in different kinds of accesses, for example, file system accesses, and also how can we detect cryptographic ransomware, which causes a lot of financial issues, like billions of dollars of damage nationally every year. So how can we detect this kind of threats, which would be anomalous accesses or cryptographic ransomwares using machine learning techniques? And then I also worked on the intersection of privacy and machine learning. So for example, privacy preserving real-time anomaly detection or privacy preserving multi-party analytics. But later, I also focused on things like ML privacy once the models have been trained. So for example, model inversion privacy attacks or the federated learning security and privacy, these topics. I have also focused on the large language model security and privacy recently. So these are more or less the more recent works from my research. But today, since we have only a limited amount of time, I will focus on these two works. The first one is the model inversion privacy attacks. And the second one is the FL, or federated learning security and privacy. So let's start with the first one. So I'm just giving you a very brief background of machine learning and its different stages. So we know that when we want to train a machine learning model or an AI model, we have to have some kind of training data. And then based on the training data, we train a model. And then once the model is trained, we can query the models using some test input, and we get the output. So that is the after training the model part. So if we look at these stages, we can identify two different stages. The first one is the training stage, where using the training data that could have been collected in different ways, and then we use the training data to train a model. That is the training stage. And then once the model has been trained, we enter into the inference stage, where we can query the model by giving some test input and getting the test output. In many cases, for example, in online training, the training process could be dynamic, which means once you train the model, it's not that you fix the model. Maybe you are learning from the environment and continuously training the model. But for the ease of purpose, I'm showing it in a two-stage way. That is the training stage and the inference stage. Now, when we talk about security and privacy, in many cases, this training data could be privacy sensitive. Also could be confidentiality sensitive. So for example, it could be trained on some healthcare data. So data have been collected from the patients, and for example, you're trying to train a model for diagnosing different kinds of diseases. So the training data that is used to train such models could be both privacy and security sensitive. There has been more research done on how to preserve the security privacy of the data in the training stage. So, for example, applying different kinds of anonymization techniques or introducing noises to the training data. We made some changes to the training data and train the models. But then once the model is trained, and let's say we removed the training data or we deleted, we encrypted all the data, and only the model is available for public to use. And this is the case in many real-life scenarios. So big tech companies, they may train these models using a lot of data that they collected, and then they can make the models public for anyone to use. So for example, a user can query the model, pay per query, and use the model. So different individuals or different companies, institutions could use those models. So the question is, once the model is made available to public, what are the security and privacy issues? Can they reconstruct some of the sensitive training data that was used to train the models, right? So that is a very interesting research question. So again, just to reiterate what I just said, so maybe sensitive training data have been used to train some models, and the models are made available for anyone to use. So the question is whether these models themselves could leak some information that was used to train the models in the first place. So this part of my research, it's again, we can call the privacy and security of sensitive training data at the inference stage, means the model has been trained, but whether the model could memorize and leak some information later. Another aspect of security and privacy in ML that I'm going to discuss today is about federated learning, or in some scenarios, it could also be called collaborative learning. So since data could be very privacy sensitive and there could be other implications, you may not want your data to end up in some central server. So this is where the federated learning came into help. It is the main motivation was privacy. So in this example, I'm showing you a very simplified case. So for example, there are 3 hospitals, and again, they want to train some model given some patient information. So because these individual hospitals' data are very privacy sensitive, it's just not possible to share the data among everyone and then train a model. So what the hospitals want to do is they want to keep the data to themselves and then train a model collaboratively. So this is done by training local models and then only sharing the local model updates with some central server that can aggregate all the information and train a global model. So as if the model is being trained on the global data set, but it's not the case, right? Each entity, for example, each hospital has their own data in their site. They're not sharing the data outside of their institution, but they are training a model collaboratively by just sharing the local model updates. So although this technique could waive the requirement of sharing or sending your data to somewhere else, we have seen that there are still a lot of security and privacy issues. And the security issue that I'm going to focus on today's talk is poisoning attacks. I will talk more about it in later slides. So think about the case that there could be a lot of individuals, a lot of entities contributing to this model, but you cannot trust everyone. So if some of these participants who take part in this federated learning algorithm, they are malicious, they can hinder the process of learning. So this is called poisoning attacks, and I will talk more about it in the later part of the talk. Okay. So to summarize, I'll be talking about these 2 main topics today. The first one is privacy and security of ML training data once the model is trained and we are in the inference stage. So the research questions that we are going to answer in this talk is, can privacy and confidentiality sensitive training data be inferred from trained ML models? So the model has been trained, the training data has been removed, but whether the ML models themselves could leak the data, and how to ensure the privacy of sensitive data at the inference phase. For the second part of the talk, I'll be talking about the integrity and the robustness of federated learning. And it again means we will be focusing on the poisoning attacks. So if a federated learning algorithm is robust against these poisoning attacks, it can provide a guarantee for the integrity. That is, the model is actually doing what the model is supposed to do, and it is not poisoned, and it is not going to give you predictions in a malicious way. So under that topic, the questions that we'll be discussing are how robust federated learning algorithms are, the state-of-the-art federated learning algorithms are against malicious participants who might be poisoning the model learning process, and how can we better protect the integrity and privacy of federated learning algorithms. Okay. So these are the two main topics, and the first one again is this one, where we'll be talking about privacy and security attacks in the ML training phase and ML inference phase, and we will be looking at the privacy of the sensitive training data. Okay, so again, just to reiterate, in many cases, with the increasing use of machine learning models, they are today trained on very sensitive training data. It could be, again, some healthcare data, some very confidential financial data, and by training the models, we are actually trying to learn from the data, and these are very useful nowadays, given that we have large volume of data. We are collecting a large volume of data from everywhere, and we can build some insights of the data by training such models. So there is no question about the utility of the models, but what we are focusing on in this talk is how can training the models on this sensitive training data could impact the privacy and security of the training data used for the training. Okay, so once we train the model, as I said, the training data is out of the picture, and then we have this model available for anyone to query. Although there could be good users, there could also be some malicious users of the model. And the main idea is that they can query the model in a way which could eventually compromise the privacy and security of the sensitive training data, and the malicious users could eventually learn the sensitive training data that was used for training such models. So there are two high-level types of these privacy attacks. One is called the membership inference attack, where the adversary is interested to learn whether a specific data point was used to train a model. So, for example, if a model has been trained on cancer patients and a user of the model can identify that this patient's data was used to train the model, it gives the adversary the knowledge that that patient has cancer. So this is a kind of privacy violation. The attack itself is a binary attack. So given a data point, whether it was used to train the model or not. Another kind of privacy attack is the model inversion attack, which not only tries to identify whether a data point was used to train the model or not, but it also wants to extract the data from the sensitive training data set. So as you can see, I have also shared the papers that came up first to talk about this kind of attacks, and they're relatively newer. It's 2017 and 2015, and more work has been done later on these attacks and defenses. So for today's talk, I'll be focusing on the model inversion attack, the second one, which is a more difficult attack to perform, and at the same time, if performed effectively, this can leak more data. So it's not just a binary attack that identifying whether a data was used or not, but it is effectively extracting knowledge from the sensitive training data and leaking information about the individuals or the institutions, whoever's data was used to train the models. And in this talk, we'll be focusing on the black box access. A machine learning model could be accessed in different ways. So white box, black box. In the black box case, you just query the model. You see nothing else. So for example, what kind of model, whether it's a neural network or decision tree, you don't have any knowledge of the model. It's just a black box. You can throw some data and get the prediction. So this is the most practical scenario because, as I mentioned, in many big tech companies, they train such models and they make it open for others to query, but they don't share much beyond the black box model that the users can query and pay for their queries. All right. So the main research questions that come out of this scenario of model inversion attacks is, does black box access to a particular model really help the adversary to estimate the sensitive attributes, which is otherwise impossible for the adversary to learn? So the main question is, now that you have been given access to the model, can you learn something more that you could not learn otherwise? I mean, if you didn't have access to this model. And is it possible to identify when a model should be classified as vulnerable to such model inversion attacks? So some models may not be vulnerable to this attacks, and some model could be. So how can we identify that this model is really vulnerable to this kind of attacks? And so that we have to be more careful in training the models on such training data. Okay, so when I talk about model inversion attacks, there could be two different types. One is a typical instance reconstruction attack, and which is more like reconstructing an instance of an image. This kind of attack more applies on the image domain. So I'm not sure how many people are there. So let's say we are 30 people here in this Zoom room, and we wanted to train a facial image recognition model. So what we have to do is we have to share our images and train a model so that given our images, the model can say that, okay, this is an image of, let's say, Sean. This is an image of Shagufta. So given that we have trained such a model, can we reconstruct some of the images by just having access to the model, right? We don't know how, let's say, a participant of this facial image recognition model looks like. So this is the actual image we can see. Let's say that one of the participants in this facial image recognition model training. And then by just having access to this model and querying the model, we can reconstruct this image, which looks very similar to the actual image, not an exact reconstruction, by the way. And this is a work from 2015. A more advanced versions of these attacks have come, and they are able to reconstruct better images. So this is the very first image reconstruction attack that has been shown, and you can see that it looks similar to the actual image, right? So this is a privacy violation. So you input your data for this kind of facial image recognition, and someone else who does not know how you look like, they can reconstruct an image of yours, which is very similar to your actual image. So this is one type of model inversion attacks. Another type of model inversion attack is the sensitive attribute inference, and this applies to different kinds of data, for example, medical records, tabular data sets, financial data, social survey data, and so on. And they don't apply to image data because here in the second type of attack, we are trying to extract the exact information. So for example, a patient's exact medical information. It cannot be a typical reconstruction, right? It has to be an exact reconstruction. So this is the goal of our today's talk. So just for an example, I'm showing you a social survey data set, and there are many such social survey data sets like GSAS and national longitudinal data sets. So these data sets contain information about individuals, and they have been asked many questions. This could include also very sensitive questions, and then they responded to the questions so that we can have a better idea of social lives. There are many applications of this kind of data sets. So there could be other sensitive data like healthcare data. I'm not going through them. I'm focusing on this data set and showing you the implications, the privacy implications of training models on this kind of privacy sensitive data. So if you have some background about machine learning, as I also mentioned in one of the previous slides, we have some X data, which is the input to the model, and also some Y data, which is the output of the model. So in this case, the last column is the output of the model, which the model would predict, given some X information, the training data, right? So as you can see that there are many columns in this data set: age, the education level of individuals, and then the Y column is the happiness in marriage. So in social survey data, the goal of the data is to estimate what is the happiness marriage level in individuals. So as you can see that there are 3 different classes: not too happy, pretty happy, and very happy. So we would like to train this model, and given some individuals other information, the columns on the left, that X, we want to get the Y value. So this is the goal of the model. So let's say that we have trained the model and we query the model using an individual's data, and we get these outputs, right? So we have 3 confidence scores, and we have 3 classes. I'm not sure if you can see my cursor, but given the individual's information, we see that this class has a confidence of 0.12, 12%. This class has a confidence of 8%, and the very happy has the confidence score 0.8, that is 80%. So the very happy class has the highest confidence, and which means that the prediction of the model is very happy for the input individual. So let's take a look at what are the data that are being used for this model training. So if you look at this column, this is a very sensitive attribute. So when the individuals were asked the question that whether they have seen X-rated movies in the last 1 month. So there are the answers to the questions from different individuals. And many of them answered yes, many of them answered no. But then the question is, once this model to predict the marital happiness is made available to the public, can a user of the model extract the sensitive attributes or the answers that individuals provided when they were asked about these X-rated movies, right? So if the individuals who contributed their data to train this model knew that their data could be leaked later, they would not have the motivation to answer to the survey questions at the first place, right? So this is the goal of this work, to see whether it is indeed possible to reconstruct some of the sensitive attribute, in this case, whether the individuals answered yes or no to the question of whether they saw the X-rated movies in the last month. So this is a sensitive attribute, and we will see that how the model inversion attacks could estimate this sensitive attribute by just having access, black box access to the model. Okay, so let's simplify this, and we will also take a look at the existing attacks and defenses. Okay, so a lot of attacks and defenses, they focused on the confidence scores, because when you have a black box access, you only have access to the predictions, maybe very happy, and also the confidence scores. So these are the main weapons for an adversary to use and to reconstruct the sensitive data. So let's see how the state of the attacks and defenses look at this information available to the user. Okay, some of the countermeasures proposed that we can give like less precise information about the confidence scores. So for example, reducing the precision, so maybe 0.1, 0.1, and 0.8. So it has been shown to reduce the attack accuracy, but not totally reduce the effectiveness of these attacks. There have been also defenses proposed that we can only share the confidence scores from the highest confidence score, but not the other classes. And also there are defenses that tried to introduce noises in the confidence scores. So for example, this confidence scores will be changed to this. So it still gives you the very happy class as the prediction, because this has the highest confidence score, but it is introducing noise so that it is difficult for the adversary to extract the sensitive attributes. So the model is giving away only the prediction and the confidence score. So if you introduce noise to that, it might confuse the adversary and reduce the effectiveness of their attacks. So given these existing attacks and the defenses, we were interested to know that what if the adversary only had the prediction labels as the output, not having any access to the confidence scores. So In that case, if the adversary is still able to reconstruct the sensitive attributes given only the labels and not having the confidence scores, and still they could do the attacks, this kind of defenses that reduce the precision of confidence scores or introduce noise to the confidence scores might not work, because the adversary is not depending on the confidence scores at all. So the question that we asked is that whether we can design a label-only model inversion attribute inference attack that does not need access to the confidence scores at all. So let me quickly give you an intuition of this attack. So the attack is called LOMIA again, the label-only model inversion attack. So the intuition of this attack is, this is the target model, right? This is a model that we are trying to extract information from. So let's say the model has inputs like x1 through xn, and the output of the model is y. And what we do here is we train an attack model to infer the sensitive attribute. So without loss of generality, let's assume that x1 is the sensitive attribute and maybe the X-rated movie question. And what our attack model achieves is that they want to train a model which is more like an inversion model that would estimate the x1 or the sensitive attribute of individuals given the other non-sensitive attributes. So we say that this x1 is a sensitive attribute which includes some very sensitive information about the individuals, and the rest are non-sensitive or could be known by an adversary, by some background knowledge, or they can collect such information. Just to give you a heads up, there could be multiple sensitive attributes as well. For example, x1, x2, x3, or more sensitive attributes that an adversary wants to reconstruct. And also the sensitive attributes could be multi-valued. It's not like a binary value like the X-rated movie question, right? So that is the example that we saw in the previous slide. In the general social survey data set, the sensitive attribute that we highlighted was the binary attribute, whether they saw the X-rated movies or not. But we have also shown that the sensitive attribute could be multi-valued as well. It might have like 5 possible values, not just yes and no. Okay, so we trained this attack model that would give this sensitive attribute as an output. So the question is, how can we train such an attack model? Okay, so here we have the same data set as the adversaries have access to. But of course, we don't have access as an adversary, we don't have access to this column, right? That is what the individuals answered to the question of X-rated movies. So how, at the first step of training the attack model, what we do is that we take each individual record that the adversary has access to, and they query the model, the target model, with different values of the sensitive attribute. So at this point, the adversary doesn't know the sensitive attributes, right? So they query the model with all possible values, the no value and the yes value. And then once they query the model with X no, let's say that they get this prediction. And when they query the model with X yes, they get the pretty happy prediction. So of course, the adversary has knowledge of the very happy. So the adversary has knowledge of the black font attributes. So from the predictions, the adversary knows that this is the right prediction. So the adversary has higher confidence that this is the sensitive attribute of this record. So this is, again, is not 100% correct. In many of the cases, it may not be correct, but the adversary can get a sense of what the value could be with a higher probability. So in our attack, what we do is that for all the instances that the adversary has access to, they query the model and get the sensitive attribute value that has the right prediction. And we do that for all the records that the adversary has access to. And in this way, the adversary can create an attack model training data set. So if you look at the left side, these are the non-sensitive attributes that the adversary has access to already. And these are the predictions that they have found from the target model. So by querying the target model many times, the adversary builds this attack model training dataset and eventually trains the model, which can give you the sensitive attribute given the non-sensitive attributes. Okay, so once the model has been trained, we don't even have access, we don't have to query the target model, but by querying this attack model and feeding the non-sensitive attributes, we can get a prediction for the sensitive attribute values. So I will quickly go through some experiment setups. We did experiment with 3 real data sets, the general social survey data, adult 538 data set. It's important to also have an idea of what data sets were used to get familiar with the kind of data sets that are used in this kind of research. We also trained different kinds of ML models, decision tree and deep neural networks. And we used the BigML platform, as I mentioned previously, that different big tech companies may make those models available after they train the models on sensitive data. So for these experiments, we used the BigML platform. Okay, so let's quickly see some attack results. So as I mentioned, the general social survey dataset was used for the experiments, and the sensitive attribute that we wanted to extract from the training data was the answer to the questions of watching X-rated movies. And these are the results for the decision tree deep neural network models. And as we see that the black ones are the results or the attack effectiveness of existing attacks, the FGR and MIA, which is the attack that was first introduced in this domain. And by comparing our results, you can see that our attacks performed a lot better compared to this state-of-the-art attacks. And they performed well in terms of recall, F1 score, and GNU. And they were consistent across different kinds of target models. For example, decision tree and deep neural network, which is not the case for the existing attack, FGR-MIA, which failed to extract the sensitive attributes for the deep neural network models. Also, these are some results of the adult dataset, another widely used dataset in this privacy in ML research. And in that case, the sensitive attribute was marital status, and you can see that our attacks outperformed the FGR-MIA attacks, again, in all metrics. So it shows that once you train the models and make them available for anyone to use, it can indeed leak the sensitive attributes, and it can leak more information than what was previously thought. As you can see with the black bars, the existing attacks couldn't perform very well, but the attacks can evolve, and we can come up with better attack approaches that can show the bigger privacy threats to such scenarios. Another interesting thing that we identified is the attacks could have some disparate impact, which means the attacks are not equal for all the groups. So for example, if you look at the first graph, the attack was effective against the male individuals with an accuracy of only 62%, but for female individuals, the attack was effective for 85%. So which shows that looking at the average attack performance may not always give you the right picture. So it is not only for this kind of research, but any kind of research. So the attacks could be, the average attack performance could be somewhere 70%, but then the attacks could be having different impacts on different groups. So for example, the female individuals are more vulnerable to these attacks. And we saw this disparate impact of the attacks, not only for the gender, but also for different races, and also for different religions, different occupations. We saw that different groups could be impacted differently by the attacks, which is a bigger threat. And we have to make sure that all the individuals have the similar kind of threat, because privacy is about every individual, right? So this is another takeaway from this work. So again, to summarize, we saw some novel model inversion attack strategies, and we saw that in the case of black box access to the models and only label-only accesses. We saw the disparate vulnerability, which is the privacy vulnerability could be different for different individuals. And if you're interested, there are more results in the paper. I will share the paper name and also the code base that is open source. So you can also play with the code base and see the results that I reported. So let's move on to the next part of the talk. And in this talk, I'll be focusing on the FL security and privacy. And this is, FL means federated learning. Many of you may not be familiar with the idea of federated learning, so that's why I'm giving you a very brief introduction to what a federated learning is. Let's take a look at a very more practical scenario. So when you are writing a message, you might have seen that the next words are being predicted. When you're writing emails, it happens. So how they are predicting the next words? Have you ever wondered? I mean, it's a very interesting thing, right? So, for example, Gmail, they are learning from our data. So whenever we are writing emails, they are learning from the data and they're training the models. So in that case, it is an example of federated learning because the data does not belong to just one central party, but the data are coming from a lot of participants. In the case of, the emails, maybe there are millions of users of emails. So all of us are the participants in this kind of training. And it could be, 10 individuals, it could be 100, it could be millions. So the federated learning, the main idea of federated learning is there are many participants and they have each some local data. And we are learning a global model from their data. So here we have an example of digit recognition. So let's say that there are n number of local participants, and they each have some images of digits. So this individual has images of 5 and 1s, and by collaborating with each other, we are trying to come up with a model that given any image of a digit, they will be able to say that what the digit is, right? So these are the training data, and let's say the participants have the labeled data. So this is a 5, this is a 1, and this individual has data of only 2, 1. So this is an example of federated learning. So each having some training data, they are doing some local training, they have some local models, and then eventually these models are aggregated by the server. So it's like a server client scenario. Okay, so it happens in iterations. So maybe after one iteration, the global model is sent back to all the participants, and they again work on that global model based on their own data, and they update their local models, and then again feed it to the server. So in this way, after a few iterations, they can converge and come up with a model that is better than what each individual could have trained on their local datasets. So that is a motivation of federated learning too. Privacy is a motivation because you're not sending your data to some other party. You can keep your data, train local models, and share only the local models, which of course has less privacy violation possibilities than sharing your local data. Another motivation of federated learning is that the global model could be more functional, could have more utility than the local models, because each individual party may have only very limited data, and those models may not work very well to perform the task. So that is a very brief overview of federated learning. I hope you got some idea. But let's look at the security implications. So since federated learning models are trained on data of unknown participants in many cases, for example, Gmail is learning from millions of people. Gmail cannot trust each individuals who are writing emails using Gmail, right? So let's say that one user of this federated learning or one participant starts putting wrong labels. So for example, they label 2 as 5, they label 1 as 7, or which is a case of untargeted puzzling attack because they are making untargeted changes. I mean, all the images could be, all the digits could be changed. There could be some targeted attacks that is maybe not changing 2, but changing all 1 to 7. So targeting a specific digits instead of all the digits. And there could also be some backdoor attacks, which means making specific changes to different images and mislabeling them to, so that in the inference phase, if you introduce this, a dot or a rectangle to the image, it is misclassified as 7. So this is called a backdoor attack. I'm sorry, I'm not being able to give a lot of details. And another kind of attack is model poisoning. So instead of poisoning your data, you can poison the models and impact the learning process of the global model. So these are called the high-level poisoning attacks. Think about a good percentage of Gmail users writing garbage emails, and then it could eventually impact how Gmail is learning and predicting the next words. If a lot of users start putting random words in their emails, the Gmail model could also be impacted, and it can give you predictions of words that do not make any sense to you. So this is how federated learning processes could be impacted by its users, because they can introduce poisonous data or poisonous models and can impact the global model learning process. So some of the shortcomings of the existing works are that propose some defenses are the server is assumed to have a clean data set, but it's not possible in many cases because the participants are the real owners of the data. I mean, if the server really had the clean data set, they could train a model by themselves. I mean, it didn't require all these participants to come and help train the model. So one fundamental thing is that used to defend against these poisoning attacks is the assumption that good models, the blue ones, would be very different from the poisonous ones, and the good models would be very similar between themselves. So for example, assumes that delta 2 and delta 3 are greater than delta 1. So delta 1 is the difference between these blue models, good models, and delta 2 and delta 3 are the differences between good and bad models. So these defenses have issue when, let's say, the participants have very different kind of data. So in that case, delta 1 could be very high too, because this is called non-IID data, which means the data distribution are very different for different participants. So in those cases, these defenses that assume that good models would be very similar and bad models would be very different from the good models, these defenses do not work, because the good models could be very different too when the distribution of the data sets are very different. So in our case, what we proposed in our solution is that we need to validate these local models. So once these models are trained, these models will be validated, and by whom? Going back to the real owners of the data in a federated learning scenario, because those are the participants are the ones who have access to the data. So we go back to them and we identify some validators and get the models validated before we incorporate them in this whole iterative process of aggregating the data to the global model. So this is the basic idea. I think we don't have much time to go over this. I will go through the main design of FL Shield that we named our defense approach. So this is again the pipeline of the federated learning, similar to the pipeline that we showed previously. But what we do here is that instead of using the local models directly, we produce some representative models. And then these models, as I mentioned, would be given to some validators to see whether the models are poisonous or not. So we randomly sample some of the local participants as the validators, and then give these representative models to them to validate. And they give us some validation reports based on the quality of the representative models. So as you can see that this model is poisonous because this participant is a malicious participant. So what we see is that these validators would give a negative result for this representative model, which means that we can reduce the weight of this model in the aggregation process. So this is how we can identify malicious inputs, malicious models, and reduce their impact from training the global model. So again, we experimented with different kinds of attacks, untargeted, targeted, and backdoor attacks that I mentioned previously. And we also evaluated our approach with Fed average, which is a very, the vanilla version of federated learning, which does not have any defense. And we also experimented with a ceiling baseline, which means a perfect defense, which knows that which ones are benign and which ones are malicious. So this gives a lower baseline, and this gives a higher baseline for our evaluation. Okay, so let's take a look at the results. As we can see from here, these are the model accuracy, how the original model works. And then these are the recalls and the backdoor accuracy. So as you can see here, the Fed oracle, that the last bar, the 4, is a perfect defense. So it knows that which ones are malicious and which ones are not. And these 2 ones are our defenses. And this is a no defense approach, the first of the 4. So as you can see that our approaches work similar to a perfect defense, which already knows that which ones are malicious and which ones are not. And we are also able to reduce the accuracy, the attack accuracy, down to around 0% compared to the no defense approach. You can see that the attack accuracy could reach like 100% if the model was not defended at all. So these are some more results. You can see the papers as well, and I would not go into the details. This is just to show you that how we can identify if a validator is a malicious and they are trying to misclassify a good model as a bad one and a bad model as a good one. So we showed that it is indeed possible to identify if a malicious validator is trying to reduce the integrity of our defense. And also we showed that by having representative models, we can also prevent the gradient inversion attacks. If the attacks were done on the local models, it would be possible to reconstruct the images, which is a privacy violation. But by using representative models, we can evade those attacks too. So the main takeaways of this discussion is that FL Shield, which is a defense against the poisoning attacks, can indeed defend against poisoning attacks. And we also designed 2 defense-aware attacks, which is the attack would know how our defense works. And the attack would have like different steps based on our defense. But we also showed that we can detect and defend against those attacks which are aware of our defense. Okay, so I will be concluding this talk here because we are almost there. These are the 2 papers that we mainly discussed, and the code bases are public, so you can download it. And also, if you have any questions, you can send an email to my email address. It's also here. So at this point, I would be happy to take any questions. Thank you so much for joining this talk. And I'm just trying to see if I can see the Q&As or not.
Yeah, thank you, Dr. Mehnaz, for the really insightful talk. So if you guys have any questions, you can drop it in the Q&A, and we can discuss them. Yeah, I guess I will get started. So I have a very simple question. So for the model inversion attack, so we know about differential privacy. So what do you think is the impact of differential privacy with model inversion attacks? Is there any way that they did, like, I just want to understand whether there can be any defense based on this, or how actually these 2 relate, or differential privacy is not useful at all in this context?
Yes, differential privacy is relevant in the case of ML privacy, but it is more relevant to this membership inference attack instead of the model inversion attack. So as you can see that there are two versions of this attack, the membership inference and model inversion. So membership inference works in the record level, whether this record is present in the training dataset or not. And differential privacy is also at the record level. So if you apply differential privacy while training the models, it reduces the effectiveness of membership inference attacks. But model inversion attack is eventually, it's looking at attribute levels, not at the record level. So it has been shown that differential privacy will not be as effective as they're expected to be when we do the model inversion attacks. But yes, it has good impact on membership inference attack. That's a very relevant question. Good question. Yes.
Yeah, thank you. Thank you. That clarifies a lot. So
Sure.
anyone wants to ask anything? It seems like I am the only curious one. Yeah, I will go for one more question. So we're talking about FL Shield. You said like if there is some adversary who knows about the defense, there as like in the paper you showed the evaluation. Can you elaborate on that a little bit more? That suppose I know that FL Shield has been deployed. What will be the impact for that? Like how much I can gain from that information?
Yeah, so in the design, I showed that FL Shield, we give the local models, the representative models to different validators, and we randomly sample some of the participants as validators. So in the FL Shield aware attacks, we assume that the validator as a malicious could be a malicious participant too, because we randomly sample. We cannot put trust to the benign ones because we don't know who are malicious and who are benign, right? So we designed some FL Shield aware attacks where the validators try to mess with the validation report. So they may identify some good models as malicious ones and the malicious ones as benign ones. So this is how we designed the FL Shield aware attacks. But as you can see from this figure, even if the malicious validators try to put like malicious validation reports, they could be easily separable because of how we designed a metric, which is called LIPC. I didn't go much details. Based on that metric, we could still identify that these are the malicious representative models, and we reduced the weight of them in the aggregation process.
Yeah, thank you. Thank you for the clarification. I think we have few questions from the audience. So
Sure.
we have one question from Nicholas Harrell. So he is asking, in the untargeted poisoning attack examples, would smoothing the labels or adding noise to the labels reduce the effectiveness of the poisoning attacks? I'm not sure if this has already been tried.
Yes, that is a very good question. So in the case of untargeted attacks, it means that the adversary is trying to reduce the model's accuracy, and they are trying to mislabel randomly. So in that case, the defenses that the person mentioned could work because when you do some untargeted poisoning attacks, it's not very stealthy. It's the local model, as you can see here, the red one, would perform very bad because the participant is trying to mislabel the data in a very aggressive way, right? So in those cases, the defenses that have been mentioned would work, but they are not effective in cases of targeted poisoning, which could be stealthy. So you are not changing the label of all your data, but some very small set. So in those cases, this red model may not be performing as bad as the untargeted attack. So here we tried to come up with a defense that could defend against all kinds of like stealthy, more aggressive, or even backdoor attacks. And we had difficulty having that without reducing the model's performance. But the defenses that have been mentioned would work better for untargeted puzzling attacks, but maybe not for the targeted and the backdoor attacks, which are still the versions of puzzling attacks. Very good question, though.
Yeah, we have, I think, a lot more questions. So I think I will just ask one more from the audience. For the others, I would recommend you can please email or contact Professor Dr. Mehnaz for more answer to your questions. So the last question is from Mazharul Islam. He asks, could you highlight how FL Shield can provide defense when the attacker is aware of the deployed defense? Oh, I think we already went through that, so I will jump to the next question.
Sure.
So Shaikh Islam asks, for the FL Shield, what's the impact of using model mimicking attack instead of model inversion? Would model mimicking serve any purpose in this context?
Model mimicking means I'm not 100% sure. Are they pointing to model stealing attacks, which means they are trying to come up with a second model very similar to the original model?
I think that is the intention. I also don't explicitly know what model mimicking attack is.
I believe it is unless the person clarifies further. So model mimicking or model stealing is a different kind of privacy attack. So think about, big tech companies, they collect a lot of data and they train such models, and then they sell the model, right? So anyone querying the model would pay them. So model mimicking is model stealing is a different kind of attack where the adversary tries to train a second model that would work very similarly as the original model. But once the adversary is able to train such second model, they would not have to go to the original model and pay for that. So by querying the model, they can come up with a data set and train a second model. So this is very different from model inversion attacks, because in the model inversion attack, it's like we are trying to make the one-way journey from data to model to the two-way one, where we are trying to reconstruct the training data by accessing the model. And model stealing would have a very different goal, I believe. So they are actually separate, very separate.
Yeah, thank you for the clarification. So let's again applaud Dr. Mehnaz for the really nice talk. For the other questionees, I would recommend you contact her if you have any questions or interest in her research. So thank you, Dr. Mehnaz. It was really nice hearing from you.
For all the questions and for giving me an opportunity to share my research with the larger audience. Again, as Imtiaz mentioned, if you have further questions, feel free to send an email, and I'll be happy to answer in that process. Thank you so much, Mike and Sean, for cooperating in this.
Absolutely. Thanks a lot. Take care.
Thank you.
Thank you.
Take care, everyone.